Differential equations are equations that contain derivatives. A first-order differential equation has a first-order derivative, and a second-order differential equation has a second-order derivative. There are some classic differential equations that can describe growth, decay, and oscillation, and I want to review them now. So let's start with growth. The simplest type of growth is called linear growth. That's when a process grows linearly. The equation for linear growth is x of t equals at plus b. So this is a linear equation. So how do we determine the differential equation for linear growth? Well, we can start with this form of x and see how we can get an equation that contains derivatives. So if we differentiate x, the b will go away and we get a. And then if we want the a to go away, we just differentiate twice. So if we take the second derivative of x, I'll represent that as x double dot, and that would be equal to 0, would be an equation for linear growth. To get back x of t, we would need initial conditions. A second-order differential equation needs two initial conditions. Here we see that if x of 0 would be x of t equals b, so we would assign that b as an initial condition, and the first derivative at t equals 0 then would be a, so we would assign that a. And that would be the equation then, differential equation, two initial conditions to give us linear growth. A stronger type of growth is called exponential growth. So that's when x grows exponentially. But we can also consider the case of exponential decay. In that case, our form for x of t is a constant, I'll call it capital A, times e to the rt. R is often called the growth rate of the system, of the problem. So this is exponential growth when r is positive, and it's exponential decay when r is negative. What differential equation does this solution satisfy? Well, we know that the derivative of the exponential function is just the exponential function. So if we take the derivative here, x dot, we would get back a e to the rt, and using the chain rule, we would drop down a constant r, so that would be equal to rx. And then to get the a in the initial condition, we would have x of 0 equal to a. So that's exponential growth, or decay if r is negative. The last differential equation I want to discover here is for oscillations. So what is the functional form for oscillations? The typical oscillation is a sine or a cosine. So we can write x of t equal to a cosine omega t plus b sine omega t. Omega is called the angular frequency of the system. Okay, so that's a typical oscillatory solution. What would be the differential equation here? Well, we know that the first derivative of cosine is minus sine, and the second derivative of cosine is negative cosine. So let's use the second derivative here. So if we take the second derivative of x with respect to time, we would get a negative cosine and a negative sine, but we pull out an omega squared using the chain rule. So x double dot plus omega squared x then would give us the second derivative would be equal to the negative of omega squared times the function. So this gives us 0. And that's the prototypical equation for oscillations. We'll see that this is called a simple harmonic oscillator equation. And what would be the initial conditions? Well, we can get cosine or we can get sine. So if we wanted to get A times cosine omega t, what would we do here? We could set x of 0, then sine would be 0, cosine would be 1, so x of 0 would be A. And then we can set the first derivative here to get b equal to 0, that would be 0. On the other hand, if we wanted the solution b sine omega t, how would we get that? Well, we would like this a to be 0, so at t equals 0, we get a, so we would set x of 0 equal to 0. And then if we wanted to get b, we would set x dot of 0. So x dot of 0 brings an omega also, so that would be omega times b. Okay, so these are two separate initial conditions. In the first case, we would get a cosine function. In the second case, we would get a sine function. So let me review. So we've looked at growth, decay, and oscillation. Two types of growth: linear growth, where x double dot equals 0, and exponential growth, where x dot equals r times x. If we're looking at exponential decay, then it's just the case when r is negative. Finally, we looked at a system that oscillates, and the prototypical differential equation here is x double dot plus omega squared x equals 0. Omega here is the angular, what's called the angular frequency of oscillation. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.